Okay, and this one we have this is on the exercises 5.1. We have a random variable that's we're given the PDF, but we have a C in there. And the function is only defined or non-zero from -1 to 1. So to find the value of C, we just integrate it from -1 to 1, which is the entire domain of X. We have this f of x here, this is our PDF, and dx. And we know that that equals 1 because the area under the entire PDF has to equal 1. Integrating this gives us a C of 3/4. We can then use that in our part B when we're trying to find the CDF. So up until we get to -1, the CDF is just going to equal 0. F of x is just going to equal 0 because there has been no probability added, I guess you could say. Between -1 and 1, we have this function 1 minus x squared, and the 3/4 is being multiplied by it, of course. So we want to integrate that from -1 to x. Now they're using the same variable here and here. I prefer to use a different dummy variable here, maybe a t squared and a dt, just so you know that this is the stopping place and this is the actual function, but as long as you're keeping those straight. We integrate that, and notice that we end up with a function, not a specific constant like we did here, which makes sense because the CDF should depend on where our actual x value is, and it does. And then it didn't ask us here, but what would f of x equal if x is greater than 1 or equal to? Well, in that case, it would just equal 1 because we've achieved the full probability for the function. So from then on out, the probability would be 1 that x is less than or equal to any of these x's we choose greater than 1. Okay, for number 3, we have a function. We also have a capital C, a constant, in our PDF, and we're asked if it could be a probability density function. The answer is no. Now, I'm not real fond of their answer because it's telling us that the function evaluated at 5/2 would be a negative number. That's true unless C is a negative number, but in that case, then the 2x would be a negative number, and that would be less than 0. So one way or the other, part of this potential PDF that they give, part of this function they give, is going to drop below 0, the value of the function. In other words, the y value, the output of the function will be less than 0, and that is not permissible for a PDF. Notice that we could arrange this so that the area under the curve equaled 1, so that's not why it fails to be a PDF. It fails because a PDF has to have the area under the PDF must be equal to 1, and no part of the PDF itself can have a negative value, a y value, which would essentially be a negative probability. And that's true, by the way, for both of the functions that they give in 5.3. Okay, here we're given a PDF for a gas, how much gas we want to keep, our weekly volume of sales, I guess. And we know that we want 90% of the time, 99% of the time, we want to make sure that there's enough gas. So really just the very final little tip of our probability function, the area under that portion should equal 1%. In other words, if we integrate from C, whatever this cutoff point is, to 1, which is the top, the highest value of the x domain, that area should equal 0.01. And then we can just evaluate this integral, and we would get 1 minus c to the 5th power, solve then for c to get this right here. Another way that you could do this, you could set 0.99 equals 0 to c, of the same function here. So basically looking at it, the part that meets the conditions versus the part that doesn't meet the conditions. Okay, here both of these parts of this problem are based on the fact that the area under a probability density function should equal 1. Actually, I take that back. Only the first part is based on that. The second part is based on the formula that we have for e of x and the fact that we know the expected value is 3/5. So starting with the first thing, if we evaluate this integral over the entire domain of x, we know that it equals 1, and that will solve to this equation right here. When we're solving for e of x, we just need to add that extra x in, which will change it just a little bit in terms of our integral that we're evaluating. Then we set that equal to 3/5. Now we have two equations with two unknowns. We can either use substitution or matrices and then put it in reduced row echelon form, elimination, any way that you know of to take two equations with two unknowns and solve for those two unknowns here.